Hi everyone, in this lecture we're going to talk about the Bohr and the quantum mechanical models. So we're first going to begin with the Bohr model. In the Bohr model, they represent the atoms with orbits. So the Bohr model is similar to the planetary model where the planets orbit the sun, but in the Bohr model, the negative electrons orbit the positive nucleus. Electrons can only be in specific allowed orbits and not in between orbits. So this is analogous to the steps of a ladder where you can't step in between steps and you have to step on the actual steps. So each of these circles here represents an orbit. Electrons can only be in these orbits and not in between two orbits. So in this Bohr model, what we see is that the first orbit holds 2 electrons. The second orbit holds 8 electrons. And notice the orbit that is closest to the nucleus is labeled as n equals 1, then n equals 2, n equals 3, and as we get farther and farther from the nucleus, the n value increases. Another thing to note about the Bohr model is that the distance between the orbits is greatest closest to the nucleus, but as you get farther and farther from the nucleus, the orbits get closer and closer together. So the n equals 2 and n equals 1 have the greatest distance between them, and as we go higher and higher up, that distance between the orbits keeps decreasing. So like we said, an electron in n equal to 2, the n is called the quantum number. N equals 2 is farther from the nucleus than n equals 1. And also note that electrons in n equals 2 have more energy than electrons in n equals 1. So the farther we get from the nucleus, the more energy the electron has. So in the Bohr model, the atoms with the lowest energy are the ones where all of their electrons are in the lowest energy state. The lowest energy state would be to be occupying the electrons from the orbit that's closest to the nucleus and then working your way up. Remember that the first orbit holds 2 electrons. So hydrogen, which only has 1 electron, when it's in the lowest energy state, which is called the ground state, that 1 electron is in the n equals 1 orbit. Helium has 2 electrons. In order for helium to be in the ground state, both of those electrons would have to be in the n equals 1 orbit. Lithium, which has 3 electrons, its ground state would be 2 electrons in the n equals 1 orbit, but the third electron has to go into the n equals 2 orbit, because after 2 electrons, the first orbit fills up. And then the second orbit, n equals 2, will continue to hold 8 electrons before filling up and going to the third orbit. So the lowest energy state, which is called the ground state, fills up the orbits from n equals 1, followed by n equals 2, then 3, and so forth. When the electron is in the lowest energy orbit, it does not give off any energy. So the ground state, which is the lowest energy orbit, is very stable and the electron does not give off energy. If an atom absorbs energy, the electron will jump into a higher orbit. We call that the excited state. The way that atoms absorb energy is through maybe heating or through lights. Like if you turn on the light in a room, all the electrons that are inside of all the atoms of the substances in the room will begin to absorb electrons. So what you notice is that this electron was in the ground state and now it absorbed energy and it moved into the excited state. In this excited state, it is not stable. So this here is an excited state. And this atom in this excited state now is not stable. Notice that that electron absorbed enough energy to go from n equals 2 to n equals 5. Okay, so here is another example of an electron of atoms being in ground state. Here, all of them are in the ground state because notice the n equals 1 has 2 electrons, n equals 2 has 8 electrons, and there are no electrons in any of the higher orbits. So the first 2 orbits were filled. Here, on the other hand, the n equals 2 still has space for one more electron, yet there is an electron in the n equals 3 orbit. So this atom here is in the excited state. So it is not um, as stable. These electrons are all in the ground state. This electron over here is in the excited state. Okay. In a higher orbit, the electron is not stable, like we said. So when it's in the excited state, it's not stable. So that electron falls back to the lower energy orbit. And as it falls back, it gives off energy as light. And that's actually how we see color. So right now, all these electrons are in the ground state. But when we give this energy, this electron absorbs that energy. Now it's in the excited state. It falls back down to ground state. As it falls back down, it releases energy. The energy that it releases is the color that we see. So if you are right now seeing this color of this electron being red, it's because the atoms that are in that electron are absorbing energy, causing the electrons in that atom to go to an excited state, and that electron comes back down to ground state, and as it comes back down, it gives off light of the red color that we see. So how much energy is actually released? The energy that's released as it goes from excited state back to the ground state is the energy difference between the two orbits. So in the case we looked at, the electron went from n equals 2 to n equals 5. The energy difference is whatever the difference is in energy between 5 and 2. That energy difference is the color that we see. So this released energy, and as it came back down, it showed a color that we would see. So in this slide, I'm showing you two different electrons that have absorbed energy and have gone from the n equals 1 orbit up to, in this case, the n equals 3 orbit. And in this case, it's gone from the second orbit to the fourth orbit. The difference in energy, or the amount of energy released, is the difference between the two orbits. So here it's 12 minus 2, so there's 10 units of energy released. In this example, it goes from 14 to 8, which is 6, so 6 units of energy was released. So more energy is released in this example than is released in this one here. Okay, so here's an example. Which of the transitions in the Bohr model releases the most amount of energy? So in this question, we're given 4 choices. When something releases energy, right, the key word here is release. When energy is being released, it's going from a higher orbit to a lower orbit. When energy is absorbed, it's going from lower to higher. So in this example, part A, we're going from 2 to 4. So this one is absorbing energy. In the second one, we're releasing energy because we're going from higher to lower. The closer you get to the nucleus, the more you're releasing. This one is also releasing. And the last one is absorbing. So since the question is asking us for release of energy, we know that it's not going to be A or D. Between B and C, it's asking for the release of the most energy. That means the greatest unit of energy released. Notice that both A or B and C are falling 2 orbits. But what you have to remember is that the farther you get from the nucleus, the closer the orbits come together. So the correct answer would be C, because the difference between 3 and 1 is greater than 5 and 3. And that's just because the orbits are initially far from each other, but as you get farther and farther out, they come closer and closer together, right? So 5 and 3 are much closer to each other than 3 and 1 are. And so more energy is released with 3 and 1. Here's another question. Two energy transitions occur that release light of visible color. If one is red, the other is green, which one is which? So red is less energetic, right? Remember Roy G. Biv, red is the least energetic, violet is the most energetic of the colors. So green is more energetic. Basically, we assign the one that's more energetic to green, the one that's less to red. Since 3 to 1 is a bigger difference in energy, remember we said the gap between 3 and 1 is much greater because they're closer to the nucleus. 3 to 1 would be green, and 5 to 3 would be red, because 5 to 3 does not release as much energy. And here's the last one, an electron in which orbit has more energy? Remember we said the farther they get from the nucleus, the more energetic they are. So an electron in n equals 5 has more energy than an electron in n equals 3. All right. So the Bohr model actually contains some error, but because of its simplicity and because it gives the correct results for a lot of the accepted features of the atomic theory, we actually still teach it to students. But in reality, the Bohr model does not really explain the full picture. The more modern and complex version of the atomic theory is called the quantum mechanical model, and it gives a better explanation of the electron behavior. So the quantum mechanical model is kind of an extension of the Bohr model. Not everything about the Bohr model is wrong, and we actually will continue to use the Bohr model to predict a lot of things. And like we said, the quantum mechanical model is an exception, it's an extension of the Bohr model, but it's really based a lot on a lot of mathematical equations. Here we're going to simplify it and actually not look at any mathematical equations to explain this model. So the quantum mechanical model has orbitals instead of orbits. And it's a 3D model rather than a 2D model, which we saw with the Bohr model. So here we have the Bohr orbit, which is two-dimensional. Here we have a quantum mechanical model orbital, which is three-dimensional. So notice this is a sphere, and this here is a circle. Let's look at what orbitals are. So orbitals are three-dimensional models of the probable path that an electron will take. So this over here shows us, the sphere shows us that an electron could be anywhere inside of this sphere at any given moment. It's not like the Bohr model where it tells us exactly the path that an electron follows. It just gives us the probable path. So why does the quantum mechanical model only give a probable path that an electron takes? Well, it turns out that light, and actually other matter or matter as well, acts as both a particle and a wave. We say that light has a dual property. It has a wave-like property and a particle-like property. So even though matter also has wave and particle-like properties, for matter, the wave-like property of it is not very significant or noticeable. But for electrons, which are actually very small, that wave-like property of them is very significant because they have relatively large wavelengths. And so those waves become very noticeable. So because waves can actually be in several different places at once, we can't really measure the location and the momentum of a wave at the same time. And so this is why the quantum mechanical model only gives us a probable path of an electron and not the exact path of an electron. So you can think of it as actually the exact um, the idea of trying to look at the path of an electron makes the electron switch places. So in order for us to view an electron and its path, we would have to shine a light on it so that we could see it. The actual shining of a light on an electron causes that electron to change its location because it would absorb energy. That doesn't happen for large objects, but it's significant for electrons. So how do we come up with the shape of these orbitals here? Well, we get those from probability maps. Probability maps, which are shown here in these two squares here, are represented by dots. Each of these little black dots that you see in each of these pictures is a picture taken each second. So they take those pictures, one per second, and they superimpose all those pictures on top of each other. And what you notice in this picture of the electron, right, one picture per second, is that it kind of looks spherical. It looks circular in two-dimensional, but in reality it's spherical. So we come up with this shape of the orbital, which actually the border shows where 90% of these dots are. So it's where electron spends 90% of its time. And then this is another orbital that we're going to talk about as well. And if we were to look at where electron spends 90% of its time, it would show us a shape that looks like this. All right, so let's look at the difference between the Bohr model orbit and the quantum mechanical model orbitals. So the orbit, which is part of the Bohr model, is two-dimensional, whereas the quantum mechanical orbital is three-dimensional, right? The Bohr model was a orbit that was circular. The quantum mechanical model, we saw one of those orbitals is a sphere. The orbits are represented by a number, by a quantum number, right? We saw n equals 1, 2, 3, 4, and it keeps getting bigger and bigger, that number, as the orbit gets bigger and bigger. With the orbitals, they're represented by both a letter and a number. The number is just like the Bohr model, but the letter actually specifies the shape. So whereas in the quantum mechanical model, or whereas in the Bohr model, we only had one shape, all of them circular, in the quantum mechanical model, as you'll see, they have many different shapes. The orbits represent a specific path, whereas the orbitals represent a region in space, a probable path. And different orbits have different radii, same shape, different radii, whereas different orbitals have different radii and or a different shape as well. So let's talk a little bit more about the orbitals and the different shapes of the orbitals. We'll start with the s orbitals. The s's begin at n equals 1, and they can go all the way up to n equals infinity. So we can have 1s, 2s, 3s, all the way up to infinity s. S stands for sharp, but you can think of them, a good way to remember is S for spherical. The shape of them is spherical because they're three-dimensional. The lowest energy orbital of all is the 1s orbital, which is analogous to the Bohr model n equals 1. The 2s is similar to the n equals, or it's similar to the 1s, except that it's slightly larger. So here I'm showing you the 1s, here I'm showing you the 2s, and here I'm showing you the 3s. Each of these orbitals holds 2 electrons. So remember that we said in the Bohr model, n equals 1 holds 2 electrons. That's why the 1s is analogous to the n equals 1 because it also holds 2 electrons. The next shape, orbital shape in the quantum mechanical model, is the p orbitals. The p's begin at n equals 2 and can go all the way up to infinity. So we can have 2p, 3p, 4p. We cannot have 1p. P stands for principal, but you can think of it as peanut because they're kind of shaped like a peanut. And they have three subshells, X, Y, and Z. So whereas we saw with the S's, there's just one, with the P's, there is three of them. So the two P's have three P's, one of them being 2px, the other 2py, and the other 2pz. They all look identical to each other. The difference between them is in their orientation. Each one of these holds two electrons. So the two p's all together hold 6 electrons. The three p's all together hold 6, and so forth. They all hold 6 electrons. One in the x direction, one in the y, one in the z. But they also all have the same energy. And then we look at the d orbitals. The d's begin at n equals 3 and can go up to infinity. So we do not have 1d, we do not have 2d, we have 3d, 4d, and so forth. D stands for diffuse. Notice that 4 of these are shaped kind of like a 4-leaf clover in different orientations. And the fifth one looks kind of like a p orbital going through a donut. There are 5 subshells, as you can see. Each of these holds 2 electrons. So the D's together hold 10 electrons. So there are a possible 10 spots in 3D orbitals for electrons. 10 in the 4D, 10 in the 5D, and so forth, as each subshell holds 2 electrons. And then we have the Fs. The shape of the Fs are a lot more complicated. The Fs begin at n equals 4. So there is no 1f, 2f, or 3fs. And they go all the way up to infinity. F stands for fundamental. And I told you guys about the shape of them. And notice that there are 7 of them. Okay? Each of these holds 2 electrons. So the 4fs hold a total of 14 electrons. Same with the 5f's, 14 electrons. Same with the 6f's, 14 electrons, and so forth. Okay, this can continue on. We can go into another letter like G. The G's will have 9 subshells and so forth, but we're not going to go anything beyond the F's in this class. So notice that the electron that's in the 2s is generally closer to the nucleus than the electron that's in the 2p, right? So if this is the nucleus, notice the 2s and the 2p's overlap with each other. But this electron that's in the 2s, on average, it's closer to the nucleus than that electron that's in the 2p. So there actually is a difference in the quantum mechanical model between in the n equals 2 quantum number between some electrons and others. The 2s's actually have less energy overall than the 2p's do. All right, so let's go ahead and learn a little bit more about the quantum mechanical model. Each subshell we said or orbital holds 2 electrons. Just like the Bohr model, the electrons seek the lowest available energy state. So they fill up the 1s first with 2 electrons, then they go to the 2s with 2 electrons, and then they go with the 2p in the 2p. Remember, there's 3 2p's. I'm only showing you one of them, but there's 3 of them. Just like the Bohr model, if an electron absorbs energy, it'll move to a higher orbital with more energy. It's going to be unstable there, so it'll be in the excited state. So notice that this 2s electron here is in the ground state. It's in the ground state because the 1s is filled, so the lowest energy state this 2s could occupy was where it's at right now. If that electron absorbs energy, it'll go to a higher energy state, and now it's in the excited state. That electron is not happy there in the 2p because there's a space available for it in the 2s. So it returns back to ground state. And as it returns back to ground state, it emits light in the process. The light that it emits is the color that we see. So here is the order of some of the energies levels. The 1s has the lowest energy, followed by the 2s, the three 2p's that we have, 2px, py, and pz, are what we call degenerate. They're the same, they have the same energy. Okay. Then comes the 3s, followed by the 3p's. And then here is where we kind of see something unpredictable happen. We would have expected the 3d's to come next, but in reality, the 4s's come next. So the 4s electrons are lower in energy than the 3d electrons. Okay, and remember there are 5 subshells for the d's, and they are all the same energy. Also notice that the gap, just like how we saw in the Bohr model, is greatest between the orbitals that are closer to the nucleus, and that gap decreases as we get farther and farther from the nucleus. All right, so here are some practice problems for you to do on your own. So you can pause this video, attempt these problems, and then on the next slide, look to see if you did them correctly. And here are the answers to the questions.